All right, here we're going to introduce the tangent vectors tu and tv to a parametric surface S and the corresponding normal vector to the surface S, which is formed by taking the cross product of those vectors tu and tv. So to begin, let's say we have a vector function r that's giving a parameterization to a surface S in R3. So here's the domain of R. It's just taking points in the UV plane in this region, and it's going to map them over to these position vectors that are just describing points on our surface S. And let's suppose that I hold V constant and I let U vary along this red horizontal line. Well, our vector function R is going to map this red horizontal line to a certain cross section of our surface. And since we're letting U vary, I'm going to refer to this red cross section as a U trace of the surface. Okay, and likewise, we could hold U constant and let V vary. And so in other words, moving along this green vertical line, now our vector function R is going to map that into another type of cross section. And since we're letting V vary, we're going to refer to that as a V trace. Okay, and so now let's say I am at this point right here and I increase U a little bit. So I move a little bit to the right on this along this red horizontal line. Okay, what's going to happen to my position vector? Well, the position vector's head is just going to move along this red U trace. And let's say I want to know the rate at which this position vector is changing. In other words, I want to know the velocity in the direction of increasing U along this red U trace. Well, for that, I should take the derivative, right, of my position vector R with respect to U. It's really a partial derivative because we're holding V constant and we're letting U increase, okay? Likewise, I could let V increase a little bit and ask how my position is changing along this V trace. And if I want the velocity, okay, along this V trace, then I want to take the partial derivative of my position vector R with respect to V. Okay, so we're going to define these vectors tu and tv to be the partial derivatives of our vector function R. So tu is just the u derivative of R, and tv is the v derivative of R. And as we just noted here, tu, right, this thing being the velocity vector, this thing is going to point in the tangential direction to the u trace, and it's going to point in the direction of increasing u, okay, at this point r of uv. And likewise, tv, this thing is going to be tangent to the v trace because it's really just the velocity vector in the direction of increasing v as we move along this green cross section. Okay, so it's tangent to that v trace. And furthermore, okay, these tangent vectors tu and tv, these things lie in the tangent plane to the surface S at the point r of uv. And so if I take the cross product of tu and tv, okay, I'm going to get this vector here in yellow. And notice here I'm following the right-hand rule. So tu cross with tv, this thing's going to point outward in this case. This vector in yellow will be a normal vector for the tangent plane to your surface, and equivalently, right, the vector here in yellow will be normal to the surface at this point r of uv. Okay, so what we're going to now do is look at question 3 on the worksheet that has us compute this normal vector and its magnitude for each of the parameterizations we went through in the table on the worksheet. Okay, so let's go ahead and do that next. Get rid of some of this stuff here. And I did include all the answers. Okay, so keep that in mind on the worksheet as we go through these. So in the case we have an explicit surface, so z is g of xy, our parameterization is just x, y, g of xy. So taking the x derivative of r, right, that's what tx is. I'm just going to get a 1, right, from the x derivative of x, a 0 from the x derivative of y, and then this is just a partial derivative of the function g with respect to x. This is gx. And likewise for ty, this is going to be 0, 1, gy. Now if I take the cross product of those two vectors, we get minus gx minus gy 1. And as a little side note here, this is something we've seen before, right? If I call the function f, which is a function of three variables, x, y, z, and this thing is z minus g of x, y, all right, then our surface here, given by this equation, z is equal to g of x, y, can be thought of as a level surface of this function f. It's just the level surface where f is identically 0. And we know that the gradient of this function f is normal to the level surface of f that passes through this point x, y, z. And if I take the gradient of this thing, I get exactly this, right? The x derivative of f is just minus gx. The y derivative is minus gy, and the z derivative is 1, right? So this agrees with something we've already seen. And we also note here the magnitude of this normal vector is just the root of 1 plus gx squared plus gy squared. We're going to see this expression come up a little bit later. All right, cool. So how about cylinders? Well, here's our parameterization that we derived in a previous video. So if I differentiate this thing with respect to u, okay, I'm going to get minus a sine u, then a cosine u, and then 0, because I'm differentiating v here with respect to u. Now if I differentiate with respect to v, I'm going to get 0, 0, and then 1. Okay, and so one quick comment here on the cylinder, if I let u vary and I hold v constant, in other words, what's my u trace going to look like? Well, remember, u is just the polar angle theta, and v is just the z height along the cylinder. So if z is constant, right, and I'm letting theta vary, I'm just going to describe a circular cross section of my cylinder. So tu is just this tangent vector to this circle here. And what's TV? Well, what's the V trace first? If I let V vary, so in other words, let Z vary and hold U, which is theta, constant, I'm just going to be moving along a line like this along the cylinder. That's just parallel to the Z axis. And TV is just the vector K, right? It's just the vector pointing in the positive Z direction of length 1. Okay, now if I take the cross product of these things, notice the direction here is pointing radially outward from the center of this circle. Okay, so if I imagine moving radially outward like this along this line, that is the direction here for this cross product vector, which really makes a heck of a lot of sense. We could have determined this direction without even having to do this calculation. But nonetheless, when you do the calculation, what do you get? Well, you get a cos u, a sine u, 0. And that's exactly what this vector is. You're really just taking the position vector on this cross-sectional circle, right? A cos, a sine, 0, and then you're moving, right, its tail, so it's starting here at where you're located on the cylinder. So that makes a lot of sense. Also note here the magnitude of this cross product vector is just constant A, which is just the radius of the cylinder. All right, cool. And so now let's go ahead. I'm going to delete out that. And let's go ahead and look at cones next. So pretty similar here in terms of the calculations. Tu is minus v sine u, v cos u, and then 0. Tv is cos u sine u 1. And if you take the cross product, you wind up getting this vector right here. Okay, now notice the similarities between the calculations for the cone and the cylinder. Okay, here V, which is again was just the Z height, that is determining the radius of one of these circular cross sections on your cone. And if I let U vary and I hold V constant, right, the U trace there is just that circular cross section. So Tu is just this tangent vector to that circle. And then if I let V vary and I hold U constant, that's just going to move me along one of these lines here, one of these generators for the cone here in green. So TV, this vector in orange, just points along that green line. And see, again, V is just playing the role of radius Whereas A here was the radius of the cylinder, and it was fixed, right? Every one of these cross-sectional circles has the same radius, whereas here, right, the cross sections have a radius that changes with the z height, or in other words, with v. Furthermore, the k component in the case of a cylinder is 0, whereas the k component on the cone, that should be negative, right? Because this thing is pointing down because the cone is at a slant. And that is what we see here with that negative v. So that makes a lot of sense as well. All right, and then if you take the magnitude of this thing, you wind up getting the square root of 2 times v. All right, cool. And then lastly, I'm gonna go ahead and make a little more space. We have spheres. Okay, now the calculation for the cross product here is a little brutal, but it simplifies a fair amount. Um, and I'm not going to go through the all the details there. It's just a brute force calculation, but the result is actually really revealing in many ways. And we're going to use this expression a lot, and there's a good reason for why we're seeing what we're seeing. Okay, so you wind up getting a squared times the sine of u times this vector right here. Okay, so one comment. This vector right here, notice, is just this thing right here. In other words, it's just the position vector on the sphere of radius a, but here a is just set to be 1. So what this is really doing is it's just the unit vector in the direction of our position vector r, okay? And then we have this factor a squared sine u out front, okay? So if I take the magnitude of this vector, this thing has magnitude 1 because it lives on the unit sphere, okay? So I'm just going to get this factor right here, a squared sine u. And this might sound a little familiar. Okay, if you think back to spherical coordinates, the area, or sorry, the volume element. Remember this rho squared sine phi factor that we had? Well, that's exactly what this thing is, except now since we're on a sphere, rho is just constant a, and we're calling the angle phi u here for this parameterization. Okay, so we're gonna see why this is appearing in the way that it does pretty shortly when we get into surface integrals. Okay, the other big thing I want to highlight here is that, as we noted, this thing is just our position vector, right? But it just has unit length, and then we're scaling it by this factor here. But the point is, this vector, right, just points radially outward from the origin, right? I mean, so its tail is placed right here on the sphere, right? But it's just pointing radially outward, and that makes perfect sense. Again, kind of like what we said with the cylinder, we could determine the direction of a normal vector for a sphere just from the geometry of the sphere, but uh, the fact that this factor here, which is related uh, to that volume element that we saw back in spherical coordinates, has a deeper relation there too. So the direction and magnitude are going to play a big role for us. But in any event, I think I've rambled on long enough. We are going to stop there. All right. Thanks so much.